What's going on, guys? This is Stigward. Today we'll be writing an internal trainer in Rust for macOS. This tutorial builds on our previous external trainer tutorial, and by the end of it you should have a better understanding of how to craft libraries in Rust and how to inject those libraries into application space in order to edit memory and have a working internal trainer. So the first thing we're going to want to do is, instead of creating a regular Rust project this time, we actually want to create a Rust library, and that's because we're going to be injecting this library similar to like a DLL injection, and we need to compile the binary so that macOS recognizes its format. And so in order to do that, we're going to use cargo new -- lib, and then we will call this internal macOS. And that's just going to go ahead and create a project for us, and then we can cd into the new project created. And so here we are in a boilerplate Rust project. However, again, this is a library, and so you'll see that it's slightly different this time. If we take a look at librs, we can see that instead of the normal hello world program, we have this public function called add, and then we have a test. Similar to our previous tutorial, we're going to go ahead and add a new crate, and that's going to be the libc crate, which will give us some standard libc functionality. And here we are inside of our cargo.toml file. You can see that we've added that libc dependency. In addition, we want to tell the compiler what type of library this is going to be. So we're going to specify lib, and then we'll say crate type, and we want it to be a cdy lib. That needs to be in brackets, I think. And so now we're actually ready to go ahead and start writing our code. And so, like I mentioned, we're going to go ahead and get rid of all of the boilerplate stuff. Now, the first thing we need to do is we need to create a new function that's going to get run when the library is injected. And so in order to do that, we can first, we need to specify a few attributes for this particular function. The first one's going to be used. That's just going to tell the compiler that even if this code appears to be unused during compilation time, to make sure that it remains in the final binary. And then we want to specify a link section. And that's going to be data mod init func. And this just tells the compiler that to run this function when we are initializing the module, the actual modules. So basically when the library itself gets injected.
Do you want to be a game hacker? Welcome to the Game Hacking 100 and 200 series. I'm JC, and I'll be your teacher, entertainer, and whatever else you need throughout your game hacking, or as I like to call it, game enhancing journey. Get all the money and XP you could ever want. Or give yourself as much defense and attack power as you want. And even become a literal god. And much more.
Now, the next thing we do is we create this static init variable, and this init variable is going to hold the function for when the dynamic library is actually loaded into the process space. And so right now we just have a blank initialization function you can see here. And so we'll just, for now, write print line, and we'll write hello world just to show how this will work. So we'll say hello world. And now when we inject this library into our Assault Cube process space, we should see hello world print out in the console. Now, Assault Cube itself is a little bit interesting just because it doesn't have the typical application structure that you might find on some native macOS apps. So if we go into our applications and we look at Assault Cube, we can see here that we have our contents similar to a normal macOS app, and then in macOS we have what appears to be our Assault Cube binary. However, it turns out that if we run launcher, this is actually just the Assault Cube launcher, and then when we click play and it actually launches, I did a little bit of recon ahead of time, and we can see in this game data directory, there's also an Assault Cube app. And if we cd into that, we see that it looks like a macOS app as well. And we can jump into macOS and see that we actually have the Assault Cube binary. And so taking that along with the command line arguments that were specified here, we can actually use the following command to run our Assault Cube app. So this is going to go into the Assault Cube app directory and run that Assault Cube binary we just took a look at. Then it's going to specify the home directory, which we saw it actually doing here. So we can see that it's the same home directory. And then each of these command line arguments is passed as well. So you see our initialization, our width, our height, and some other stuff. And when we run that, we actually get our Assault Cube application running, which is what we expected. So back in our project directory here, we need to actually go ahead and compile our library. Now, this is actually an Apple Silicon device, and so it runs an ARM64 architecture. However, Assault Cube, in slightly confusing format, was originally compiled for x86-64, and then it uses a translation layer on the Apple Silicon to run on ARM64. And so all of that is to say that we actually need to compile our binary to target x86-64, and then Assault Cube and the M3 here will take care of the actual translation layer. And so to do that, we're going to run cargo build, and then we will make this a release version, and then we want to target x86-64, and then it's called Apple Darwin. And if you don't have that, what you can do is you can run the command rust up add x86-64 Apple Darwin, and that will just add this to your toolchain, and then it will become a target that you're able to use on compilation. And so we've gone ahead and we've compiled our library, and so we can jump back into our Assault Cube, and we will get that command pulled back up here. So we have the Assault Cube app that we ran earlier. And now for injecting our binary, we're going to use a slightly older technique. And the reason that this works is because the Assault Cube application is unsigned. However, if the Assault Cube application was signed and these permissions for a insert libraries was not explicitly outlined in the plist, the info plist here, this wouldn't work, and we would have to use a different technique. There are some other techniques you can use, specifically an injector that's been making the rounds recently, where you can actually disable SIP on your machine and then get it to work. I didn't want to do that in this case, and thankfully Assault Cube plays nicely with this tutorial. But again, this is a slightly outdated technique for injection, but you will find that it still works on a good amount of apps. And the technique in question is very similar to the LD preload on a Linux box. It's just we're going to say, let me add a space here so that it's easy to see. And we'll do dyld insert libraries, and then we're going to insert our library. Cool. And so what we've done here is we've just provided the insert libraries, and then we have actually given it a path to our library, and then we are running Assault Cube with the command line arguments that it needs in order to launch. And when we do that, we see that our hello world was actually printed initially. So our library was successfully injected, and then we continued down with the rest of the initialization stuff, and the application was launched. So at this point, we actually have a library operating in the address space of Assault Cube. So jumping back over into our code, the first thing we want to do is we actually want to create a new thread in this initialization function that's going to handle the logic for our internal cheat. And we can do that in Rust by first using thread spawn, and that will auto import some stuff for us. And now the first thing we want this thread to do is we actually want it to just sit and wait for us to tell it to continue with the cheat's logic. The reason for this is because we are going to, similar to the external tutorial, write a God mode cheat where we patch the health value, but we don't want to actually start dereferencing pointers and patching values until we're inside of the game. Otherwise, we might try and deref a null pointer or deref something that's not yet initialized, and that will cause a seg fault. And so we're just going to tell this thread to wait for our input in order to continue with the cheat logic. Okay, so we have gone ahead and created our new thread, and then we have basically assigned a new variable called stdn to IO_stdn, and then we just iterate through. This is some standard Rust for getting user input and waiting for user input. So this will just sit in the terminal and wait until we've provided any input and hit enter, and then if it is able to read that input, it will just print command has been received and to run the cheat, and if it can't, it will error out. And so what we want to do now is create a new function, and we can call this driver. And what driver is going to do is handle the actual logic for our cheat, similar to if it were like main. And so we will call into driver once we have received a command and we're ready to start running the actual logic. And so for our cheat, very similar to the external trainer, the same general logic is going to apply. The first thing we want to do is actually find the base address of the module. Only this time it'll be a little bit easier since we're already operating in the right address space. And then after that, we will just go through each of the offsets that we found in the last video and use them to patch the health. And so first things we need to figure out how to do is, like I said, find that base address, and we can do that with some Mac specific functionality. In particular, we're going to use these two library functions, dilid get image header and dilid get image name. These two functions just allow us to get images based on the name and then actually get a pointer to the base address. So we can use get image name to find the name of an image. In this case, it will be Assault Cube. And then once we find that, we can get that image's header, which will return a base address. And so what I've done here is I've just gone ahead and said we're going to use some external C libraries. We're going to use some external C functions, and in particular, we've gotten dilid get image header and dilid get image name, which are the ones that I mentioned previously. I also grabbed dilid image count, which will just give us the number of all of the images loaded into this address space so that we can iterate through them and quickly find the one that we're interested in looking for. And so now we can define a new function called get base address. It will return an option of type usize. And so what we want to do is we want to get the total number of images in address space. And then normally what we would do is we would actually iterate through each of these images. We would get their name, and then we would compare their name to the name we're looking for, in this case, Assault Cube. And if we find that, we would then get the image header, and that would be our base address. I took the liberty ahead of time of listing out all of the images, and I noticed that Assault Cube is always at index 0, so it's always the first one that's returned. And so to save a little bit of time, we're just going to operate under that assumption. So we can say let image name equal, and then we'll say unsafe, and we want C string from pointer, from pointer, and the pointer is going to be dilate get image name at index 0. And then we actually need to unwrap that from the C string, so we can say let image name. And we don't actually need the image name. This is just for debugging purposes, but we can say let image name C string toStir dot unwrap or, and we'll say unknown. So if it can't locate the name, we'll just have the name be filled as unknown. And so then we're just getting the image header in the same way we got the name, which is by using that library function and passing it index 0. We'll do a little bit of debugging here. And then we will just go ahead and actually return our image header. And so from our driver, we need to create a new variable called base address and assign it to the return type of getBase address. And then from here, we just need to actually patch the health value. And that's going to look almost identical to the way it did in the external cheat. But this time, we're not going to use an external library. We're just going to manually dereference the pointer values and write to them manually as well and just operate on raw memory. We need to grab our health offsets from our research in the last video. So I'll just do that and fill them in here. And then we need to create a new function called patch health. And that's going to take in our offsets, which is a vec of type usize. And then it's also going to take in our base address, which is of type usize. And so we first want to create a new variable called current address, and that's going to start at our base address. And then from there, we want to loop through each of our offsets. So we'll say for index in 0 to offset.len. And the first thing we want to do is we want to create a new pointer to the value at our current address plus the corresponding offset. So we'll say let pointer equal current address plus offsets at index. And then we need to convert that to a mutable U64 value. And from there, we'll print out a little bit of debugging just to make sure that we are doing things properly. And then we'll say current address. We'll assign current address to whatever is equal to the dereferenced pointer as a dereferenced mutable 64. We're just going to mark this whole function as unsafe because what we're going to be doing 90% of the time is unsafe. So and then I forgot, we actually need to convert our base address to a type of mutable U64 as well, because you can't actually dereference usizes. And so this should... and so what we can do on the final iteration is we can say that we want our health value equal to 9999. And we will go ahead and say our current address, or dereference our current address and say at that value, we should write our health val. And so I actually made a quick mistake in our cheat. So you will notice here that we were actually looping through all of the offsets, which means at the very end, we were trying to dereference our health value. So you can see I looped through them while testing, and I'm actually trying to dereference the value 100, which will obviously segfault. And so what we want to do is we actually want to loop through our offset length -1. We can find the final mem location the same way we were finding it in the loop, just by taking the current address and dereferencing it with the addition of the last offset. And then we will print out our current health value just by dereferencing mem location to make sure that that looks good. And if it does, we will go ahead and assign our 9999 to that value. And so we can compile this now just by building it the same way we've been building it, and then we can actually jump into a new game by loading it the same way we did in that previous command. I'm just going to jump into an empty map, specifically on AC Africa, and we will find a grenade here. And so we have our grenade. We see that our health is 100. If we run our command here, it doesn't matter what we type. I'm going to type run because it's cool. We can see that our current health was OX64, which is 100 in base 10. And so it should have been patched to 9999. And if we throw this against it, we will see that we now have a 9939 health, indicating that we took whatever that is, 61 damage, and that it was all the way turned up. And so at this point, it actually works. And again, last time we left the exercise to the reader to turn this into a fully functioning cheat. And I think that that's another good exercise here. You have all the fundamentals here to continue building out this functionality, and I encourage you to do so. That's going to be it for this video. Thank you so much for tuning in. If you're enjoying this macOS series, please do let me know. I'd love to continue making some of these. And yeah, I'll see you next time.